Okay, I'm going to show a simpler problem from earlier in the chapter 1. I'm going to use number 39 in section 1.2. Let me see what page that is. That problem is on page 35. It says we have a 5-gallon bucket full of pure water. All right, I better get myself a bucket. V is equal to 5 gallons. This is pure water. Suppose we begin dumping salt into the bucket at the rate of 1/4 pounds per minute. So we're talking about stuff going in. 1/4 pounds per minute. Also, we open the spigot, so I think what they're talking about is that there's a way to get some stuff out of here down here. And that would be stuff coming out. What does it say? 1/2 gallons per minute leave the bucket. But we add pure water to keep the bucket full. So at all moments in time, the volume of the mixture is 5 gallons. That's a bad 5. Whoa. So what that would mean is we would have an amount of salt in there, but they said at the very beginning it's full of pure water. So at t equals 0, the amount of salt in the bucket is 0 pounds. So we're going to use big A to hold on to the amount of salt we have. And to solve using differential equations, we would want the rate of change of the amount of salt in the bucket. So that is going to be dA dt that we're interested in setting up a formula for. I think that the amount of salt will be in pounds and the amount of time will be in minutes. Pounds per minute for everything so it can keep track of our units. So we do have pounds per minute going in, 1/4 of a pound per minute, but we do not have pounds per minute coming out. We have gallons per minute coming out. So what we can do is set up a conversion here so that we can cancel gallons and get pounds. But how many pounds per gallon are in this bucket? Well, it keeps changing because we're constantly adding salt and we're constantly removing stuff. What I would say is that every moment in time there's 5 gallons. If this volume was changing, then we would have to have a formula for what is the volume at any moment in time. But they've tried to make this number 39 problem a lot friendlier than some of the ones later. And the amount of salt in the bucket, well, we don't know what that is, but that's supposed to be what A stands for. So up here we could have said A actually means A of T, which is the amount of salt at any moment in time. Oop, I almost got off the top there. So if we use A as the amount of salt, we could just write A here. And I wonder what this works out to. The gallons cancel, and we get some sort of an answer in pounds per gallon. No, sorry, pounds per minute. The top is 1 times A is A. The bottom is 2 times 5 is 10. And that's going out, so we're going to lose A over 10 pounds per minute. So dA would be in pounds, dt would be in minutes, 1/4 is in pounds per minute, which matches, and A over 10 is in pounds per minute. So everybody's in pounds per minute, and we can feel better about this. We'll just write this in a cleaner way. we'll get a 1/4 minus a over 10. Now, in this chapter, they had taught us to try to separate variables. We want the variable a with the dA, and we would want to, if there were any little t's in this problem, we would want those with the dt. And we especially want dA on one side and we want dt on the other. So I don't particularly like having these fractions. So I think I'll find the least common denominator for 4s and 10s, which I think is 20. And I'm going to multiply both sides by 20. On this side, we'll have to use the distributive law. Also, I don't want dt on the bottom on either side. So to get it off the bottom, not only will I multiply by 20, but I'll multiply by dt. And that will also, I'll just leave it on the end here. So what we get from this is dt cancels. And then we have 20 dA. So I'll rewrite this. 20 dA is equal to 20 times 1/4, which would be 5, and then 20 times negative a over 10 would be negative 2a, and then the dt is stuck to this. So we have 20 times dA is equal to 5 minus 2a times dt. At that point, you could try to get the a's over here with the dA's, and you could have division by 5 minus 2a on both sides. So what happens is these cancel and you get a 1 times dt. So we're going to have to do some integrating to solve that problem. I'm going to bring in another sheet here. We're going to have the integral of 20 over 5 minus 2a dA is equal to the integral of dt. Now, this 20 is a constant that you can bring out of the integral, but to handle this in calculus class, probably Calc 1, they would have taught u substitution. So you'd have a 5 minus 2a would be your u. That would mean that du is equal to negative 2 dA. But we need to replace the dA with things made out of du here. So I'm going to divide by negative 2 on both sides. And I get dA is equal to negative 1/2 du. So now this thing can be replaced by negative 1/2 du. And the negative 1/2 can also come out with the 20. So we get 20 times negative 1/2 times the integral of 1 over u du. And then when we integrate dt, we get t plus c. And these numbers are bothering me. These multiply out to be negative 10. So I can divide by negative 10 on both sides. So what I get is the ln of the absolute value of u is equal to negative 1/10 t plus, now this would be negative c over 10, but that's just some other c. Okay, now what they say is that you can make the ln go away if you do e to the power. So e to the ln of the absolute value of u is equal to e to the negative 1/10 t plus c. And the e and the ln cancel, so we get the absolute value of u is equal to e to the negative 1/10 t times e to the c. This expression can be multiplied out and you have that. So that would prove that that is equal to this. but then this is equal to some other constant. So we just get c e to the negative 1/10 t. And what in the world was u? Well, back up here, u was 5 minus 2a. So what we seem to be getting is that the absolute value of 5 minus 2a is equal to c e to the negative 1/10 t. Now, if we want to remove the absolute values, we would get 5 minus 2a, and then if that is always supposed to be positive, it turns out that e to the, well, sorry, this expression could be positive or negative, but this expression could only be positive. It turns out that you can make this side always be positive if you have a positive constant here for c, because e to the power is always positive. It's never negative or even 0. So we don't have to worry about those absolute values now. And what we'll have is 5 minus 2a is equal to c e to the negative 1/10 t. Now, if we go back to the beginning of the problem, at the beginning we had pure water. And pure water means that at the beginning, when t was 0, the amount of salt would be 0. So now if I come back to this work, I can try to figure out the value of c. I can say that when t is 0, a is 0. So I'll have 5 minus 2a is equal to c times e to the 0 power, which is actually just c, because e to the 0 power is 1. And then that would allow me, oops, I forgot to plug in for a. 2 times a would be 2 times 0, and you'd get 0. So now we know that 5 is equal to c. Okay. So we do want to go back and answer all of the questions that they asked. On number 39, they asked 5 questions. What's the amount of salt in the bucket after 1 minute, then after 10 minutes, then after 60 minutes, after 1,000 minutes, and after a very, very long time? So we do want to solve this for a, and then try to answer those questions. Since I have room on this paper, I think I'm going to bring this work back up here. If 5 minus 2a, let me put a separator in here, is equal to 5 times e to the negative 1/10 t, because c was 5, then I can solve for a. I can minus 5 on both sides and have negative 2a is equal to 5e to the negative 1/10 t minus 5. Then I can divide by negative 2 on both sides. So a will equal negative 2.5 e to the negative 1/10 t plus 2.5. So for part A, the amount of salt after 1 minute would be negative 2.5 e to the negative 1/10 plus 2.5. I believe a calculator will give us that. Negative 2.5 e to the power negative 1/10 plus 2.5. We hear 0.238 pounds. B was 10 minutes and C was 60 minutes. Well, what's going to happen is when we plug in t, this time we're going to plug in 10. So we would end up with negative 2.5 e to the negative 1/10 times 10, which is negative 1, plus 2.5. So if I get this expression back and then change this to be -1, I get 1.58. So if we wait 10 minutes, there will now be 1.58 pounds in there. If we plug in 60 for t, -1/10 times 60 would be -6. So we would have -2.5 e to the -6 plus 2.5. So if I get in here and change this -1 to a -6, 2.49. Now there is a pattern here. What's going to happen is as t gets larger, you'll get large times negative is negative large, and e to the negative large is going towards 0. And -2.5 times 0 is going to head towards 0 here. So you're going to approach 0 plus 2.5. If you'll notice, these results are getting closer and closer to 2.5. When you do d, a after 1,000 minutes, you're going to have 1,000 times -1/10 is e to the -100 power. That's ridiculous. -2.5 e to the -100 plus 2.5 is approximately 2.5 pounds. And then e, when they say a long time, they mean take the limit as t approaches infinity of a of t. Now that thing would be the limit of this thing as t approaches infinity. So what we're going to get is -2.5 e to the -infinity plus 2.5. And that is going to be -2.5 over e to the infinity plus 2.5. And e to the infinity is 0. And 2.5 over 0 is, e to the infinity is infinity. And 2.5 over infinity is 0. And 0 plus 2.5 is 2.5 pounds. So once we have a formula for a, then we can whip off all 5 of these answers using that formula.